Hello, welcome to part 6 of the video series Linear Regression, a Linear Algebra Perspective. Today, we are finally going to use linear algebra concepts discussed in previous parts of the series to derive the regression line. Let us start off by having a look at the following equations. 4x plus 2y is equal to 20 and 5x plus 3y is equal to 27. A solution for these two equations can be found by using basic algebra. Over here, a solution would mean values of x and y that would satisfy both equations. And for this set of equations, the solution is x is equal to 3 and y is equal to 4. Both the equations can also be represented as lines, as you can see over here in the graph. And in the graph, you'll see that the point at which these two lines intersect is the solution to the two equations, which is x is equal to 3 and y is equal to 4. Now, let's add a third equation to this set of equations. 7x plus 2y is equal to 29. The solution that has to satisfy all the equations now has an additional set of constraints. What you'll notice is, though, that this line too satisfies the same solution because 7 times 3 plus 2 times 4 is equal to 29. And even in the graph, you'll notice that this new line also intersects the other two lines at x is equal to 3 and y is equal to 4. However, as we keep adding more equations to the set, we are adding more constraints for the solution too. Hence, it starts becoming difficult to find a single solution that satisfies all equations. For instance, let's add a fourth line to the set. X minus y is equal to 0. In the graph, you'll notice that x minus y equals to 0 does intersect with the other three lines, but not at the same point. Therefore, all four lines don't intersect at a single point. There is no one pair of values of x and y that satisfy all four equations. Okay, now let's have a look at this in matrix form. This is how all these four equations would look in matrix form. This equation results in no solution for x and y, and it is therefore called an inconsistent system of equation, just for your information. In the matrix, what you'll notice is that A, the matrix A, is basically the representation of the coefficients of x and y in the equations. So all the coefficients of x in each equation is represented as the first column of the matrix A. All the coefficients of y in each equation are represented as the second column in the matrix A. Okay, and the vector x represents the two solution that we have to find out. And on the right hand side, you can see all the actual solution values the same as they are even in the equations. That's 20, 27, 29, and 0. Now what we're going to do is, we're going to edit this equation a little bit. Instead of the right hand side values, that is the values in the vector b, we're going to substitute those values with variables. So if you look over here, the vector b now has b1, b2, b3, and b4. So we are still keeping the same equations, but on the right hand side of the equal to, you can notice that even in the four equations written, we are just substituting the numerical values with b1, b2, b3, and b4. Okay. Now my question to you is this. What values for this vector b would give a solution to the matrix equation? It's something I've talked about very briefly in one of the earlier parts of the series too. Take a pause, think about it. The answer is that b should be a vector in the column space of A. In case you're not familiar with column spaces, I would recommend watching that video first. I'll put a link to it in the description box. Okay. Now to help you understand better why the vector b being in this column space of A helps get a solution to the equation, let's have a look at an example. Let's say we added the two columns of the matrix A. Okay, so over here you can see 4, 5, 7, 1 is the first column, 2, 3, 2, and minus 1 are the second column. We're just adding corresponding values to get 6, 8, 9, 0. And let us use this resultant vector 6, 8, 9, 0 in place of the b vector in the equation, something like this. In this equation, you'll also notice that x being equal to 1 and y being equal to 1 satisfies this entire matrix equation, thus proving that B is nothing but a linear combination of the column vectors of A. And similarly, B could be any linear combination of the two columns and you would get a solution. An easy way of thinking of it is this, that x times column 1 plus y times column 2 is equal to the vector B, where x and y are any scalar values. Let us now connect this with linear regression. I have also put a link to the video that discusses the intuition behind linear regression in the description box. I'd recommend watching that first. Okay, we're now going to reuse an example from other videos. Let's say that the cost of a house is dependent on two variables, the number of bedrooms in the house and the floor the house is on. So we could create an equation of this form, that C is equal to x naught plus x1b plus x2 times f, wherein C is the cost of the house, x naught is the constant value in this equation. It is equivalent to C in the equation y is equal to mx plus c. X1 is the coefficient of the number of bedrooms, which is represented by B. X2 is the coefficient of F, which represents the floor the house is on. Now, let us create a set of B values and F values that basically represent the different bedroom and floor values for different houses. So, what you'll notice over here is that the second and third columns of the matrix A represent these B and F values, that is, bedroom and floor values. And the first column is a vector of ones. Let me tell you why we have used this vector of ones first. Okay. So if you notice, all the B's in the second column are connected to the coefficient x1. And all the F values, F1, F2, F3, F4, are connected to x2, the coefficient x2. But is x not connected to any variable? No, it's just a straightforward constant value, which is why, so that x naught can be used in each equation, we add a vector of ones. Okay. Now, in the matrix equation, we also have the original cost values corresponding to every pair of B and F values. So C1, C2, C3, and C4 represent those cost values. For example, just so that you can understand this better, C1 would be equal to x naught plus x1 B1 plus x2 F1. Okay, and similarly, you'll see that for every equation. I've written it down over here too. Okay. Now we start with this premise that there is no solution for this matrix equation. Exactly what we had said earlier in the discussion, earlier in the video. Meaning that there is no set of values for x0, x1, and x2 that would satisfy all these four equations. We are starting off with that assumption. Okay. This means that we have two very big unknowns to be found. Number one is the cost vector that would lead to a solution to this matrix equation. Yeah, it's similar to what we said, that what B vector, what our right hand side vector can give us a solution to this matrix equation. So what do? We create a new cost vector that best represents the original costs but lies in the column space of A. The next question is, how do we do it? And the answer is, we project the original cost vector in the column space by using this equation. The new cost vector, or C new, is equal to A times A transpose A the whole inverse times A transpose times the old cost vector, or C old. Over here, A is the same matrix that contains the B, F, and 1 column vectors. To understand how we came to this equation, you can watch parts 4 and 5 of this series. I'll add a link to them too in the description box. Another interesting point over here is this, that this new cost vector that you're creating, that's a projection of the old cost vector in the column space of A, is basically the predicted cost values of this linear regression model. How cool is that? That just by using this projection, you're getting the predicted values. And these predicted values can eventually be used, to find how good this matrix equation is, or how good your coefficients are going to be for this linear regression model. Okay, so this takes us to the second unknown, which is the solution to the matrix, that is finding the values of the constant and the coefficients, which are x0, x1, and x2. This can be done using the equation x is equal to A transpose A the whole inverse times A transpose times the old cost vector. This equation too has been derived in parts 4 and 5 of the series. Okay. So now that we have x is equal to x naught, x1 and x2, we have found out these three values we needed. We have our new cost vector also. Now, what is its use? Let's even talk about that a little bit. Now that you have the coefficients, okay, let's say you went to a new house. You have a new house, you know the number of bedrooms in that house, and you know the floor that house is on. How can you predict the cost yourself? By using this equation. Just substitute the bedroom and floor values in the equation cost is equal to x naught plus x1b plus x2f. You already have x naught, x1, x2. You substitute the values for b and f, and you get the cost. And that's it. There it is. We have derived the regression line using linear algebra. So thank you for listening in, and do let me know if you have any questions that I can help out with, or if you have any inputs on these concepts, and see you in the next video. Bye bye.